Partnerships have been the key to success of many of NASA, NOAA, DOE, ESA's programs, but they're also a challenge. One of the big challenges is when you deal with federal budgets and international national budgets across international agencies and countries is keeping them all synchronized. Space Station is an example, keeping the ESA budget, the Russian budget, and the U.S. budget synchronized, so all the pieces come together was a major challenge. NOAA, the budgets on NOAA and NASA trying to, the weather satellite program, there's always a desire to put new technology on board, and the new funding for new technology doesn't always get to be right in the proper phase for the instruments to be ready to be flown on some of the NOAA weather satellites. But the partnership between NOAA and NASA goes back many years to make a highly successful GOES and polar orbiting satellite weather program. We have a speaker here who's going to represent DOE and an intersection of space-based and ground-based high-energy physics. Partnerships between NOAA and NASA in these endeavors and the connection between the research programs are fundamental to achieving advances in particle physics and high-energy physics. And we'll have a speaker address that, and Kathy Turner will address that. And finally, Bill Smith of AURA, in AURA's role as the head of Association of Universities, they have several challenges. Number one, of course, is the universities themselves and keeping that partnership intact so they can represent them, but more importantly, representing the science community, and my experience has been with them in both ground-based and Hubble and JWST, but ensuring that the science community is represented and its needs are understood, and it's maximizing the utilization of tools like the Hubble Space Telescope on ground-based facilities, and as well as the promise of JWST. So all of these are partnerships that of different forms and different varieties, but I think as you'll hear from each one of them, there have been challenges, but I think you'll hear also that they've been instrumental to success of some of these programs. Starting off is Charles Baker. Charles Baker is he's the official title is really the Deputy Assistant Administrator for Satellite and Information Services at NOAA, responsible and the Chief Operating Officer for NESDIS, which many of you know, the National Environmental Data and Information System. He's also the Acting Director of the Office of Commercialization. Without any further ado, I'm going to
Good afternoon. It's always great to be in a meeting with Joe. I usually see him on the other side of the fence on an independent review where he's telling us what we've done wrong, what we can fix, and what we can do better at making environmental satellites work. And he does that quite well and quite independently, so if he capitalizes the word independent on his business card, it's for a reason. Next slide. 51 years ago tomorrow, NASA, then a very young agency, launched the first weather satellite, April 1st, 1960, Tyros 1, which is spelled wrong up there. I had 3 people proof these slides because I'm a terrible proofer, and yes, I think it might have been spelled right, and one of these Microsoft programs fixed it. But the important thing, though, was like many other projects that NASA has undertaken, it wasn't just for their own benefit as an agency, but for the benefit of the American public by means of another government agency. In those days, the Weather Bureau, part of the Department of Commerce. All it took was a few glances at those pictures of clouds from above at several hundred miles up and being able to see for the first time entire weather systems in a single image. The Weather Bureau became hooked. and has been dependent upon meteorological satellites ever since. So a year later, President Kennedy requested $53 million, note that number, for a satellite system for worldwide weather observation. Such a system will be of inestimable commercial and scientific value, and the information it provides will be made freely available to all the nations of the world. But I love this quote for several reasons. One is that he thought you could build a satellite for $53 million was remarkable. Actually, that was a system. These satellites didn't last very long in those days. The fact that the commercial and scientific aspects of the undertaking were recognized from the very beginning was important. And we have been struggling in various forums in this government and around the world to advocate the cause of full, open, timely, and free or nearly free exchange of environmental information, and to suddenly discover that President Kennedy said it more eloquently 50 years ago than we're saying it today is quite a surprise. Within months, by the way, the Congress did not appropriate the full $53 million, only $48. As usual, they knocked the number down to take out some of the management reserve. None of you have ever had a management reserve, I can tell by looking at you. But that launched a partnership between NASA and the predecessor agencies that evolved into NOAA that has endured for 5 decades. It resulted in 38 low-orbiting satellites. Let's go on to the next slide. 15 geostationary satellites. 10 of those satellites, 5 of each, are still flying today. One of those low orbiters is the operational afternoon satellite. 2 of those geostationary are the operational east and west GOES satellites. 2 more are the next round of east and west. They're in storage. And 1 is the former east satellite, now moved further east so that in its dying days it can provide support to South America, because the nature of technology lag in 15-year space systems is such that hurricane season right now forces us to do our scans in such a way that we basically drop the southern hemisphere when there's a hurricane present. And so having that older satellite looking south makes up for that lack. It's been a tremendously successful partnership in both in terms of the satellites that have flown, but I've recently had occasion to come to a couple of gatherings over at the Goddard Space Flight Center where I have met individuals from NASA who have worked on the NOAA programs for as long as 4 decades in the case of one individual. And so there are people who love these programs and feel a burden for forecasting the weather in an ever better fashion and using the space capabilities to contribute to that. Next slide. As we move into the future, we find ourselves back at the same juncture that we were at 50 years ago when we negotiated that first agreement with NASA. GOES-R and JPSS each have their own management control plan and interagency agreement that, and they're not the same as each other, which is a long and complicated story, but the fact is the agencies have had to put their heads together, many heads together, to wrestle through the problems of how do you manage a program where one agency budgets the money, another agency awards the contracts, and is accountable for delivering a successful satellite, and then the first agency takes over operations and runs the satellite for the rest of its life. And those are complicated issues, and GOES helped us work through them on the GOES-R program. And I know there are
folks in the room representing some of the companies who are the beneficiaries of this partnership. But the theme of this panel is partnerships that matter. And I want to tell you that the number one partnership that matters to my agency is the partnership with NASA. And we thank NASA for all of its contributions to NOAA satellites over the last 51 years. And we look forward to continued success jointly into the future. Next slide. NASA is not our only partner, however. We realized some years ago, more than 15 years ago, that satellites were increasing in price far more rapidly than budgets were increasing in size. In fact, those of you who work with DoD know that this has been a horrible problem over there. And so for us, one of the quickest and most obvious solutions was to partner with other spacefaring nations who fly meteorological satellites.
And so our first partnership has been with Europe, with the European Meteorological Satellite Organization. And since 2006, we have, although the agreement is much older, but since 2006, we have been operating under an arrangement where EUMETSAT flies in the morning orbit for the low orbiters, morning orbit being defined as when the satellite crosses the equator, and NOAA flies in the afternoon orbit. That means NOAA, who used to have to buy a satellite and fly it in the morning orbit, no longer has to. And the Europeans, who had been planning to buy a satellite for the afternoon orbit, no longer have to, because we exchange all of the data between the two agencies. We also use some EUMETSAT instruments on the NOAA satellites, and EUMETSAT uses some NOAA instruments on its satellites. This gives you lots of benefits, the number one being cost savings on both sides. It gives you common technologies and the ability to experience technological advances, because quite frankly the Europeans have a better sounder than we have on our low orbiting satellites, and they also have a scatterometer, which we do not have. So we're making use of that more advanced data in ways that we could not do where we simply fly in another POSE satellite in the morning orbit. And then common data to be used for weather, climate, and oceans, which allows people like the environmental modelers in the National Weather Service and their European counterparts to talk the same language because they're processing the same data. With geostationary satellites, we exchange data between our GOES satellites and Europe's Meteosat satellites, although the benefits aren't as great there for the simple reason that GOES is over the US, Meteosat is over Europe and the Middle East. So the data is not as of great interest to us as the polar orbiting data, which is worldwide in coverage, including over the US by the European satellite. But more importantly, there's a satellite backup agreement that says if we run into trouble and can't fly two satellites over the US, and Europe has a spare satellite or the capability of quickly launching a satellite, they will do so in order to help us, and vice versa. And that agreement became very useful when GOES 7 became our only satellite on orbit 20 years ago, and hurricane season was approaching. And so the Europeans loaned us Meteosat 3, which operated over the east coast of the United States so that GOES 7 could be moved westward and extend coverage out to Hawaii and beyond. And much of our hurricane forecasting for several years took place by means of the loaned European satellite. So again, a partnership that matters to NOAA. Next slide. Another partnership which has more partners involved is for satellite altimetry. The satellite currently known as Jason 2 is flying, Jason 3 is being built, and that partnership includes the French Space Agency, EUMETSAT, NOAA, and again, NASA. So we're making use of that data, which is useful in monitoring sea level rise, one of the key impacts of climate change. It also helps us forecast hurricane intensity as it detects not just the sea surface temperature, but the ocean heat content. Next slide. We're also a member of numerous international organizations, and some of these are devoted towards current issues such as CGMS, the Coordinating Group on Meteorological Satellites. Others are involved in long-range planning, such as CEOS, the Committee on Earth Observing Satellites. Yet another is focused on weather applications, the World Meteorological Organization Space Program, and others are focused on the free, full, and open exchange of data, such as the Group on Earth Observations. Next slide. In addition to the traditional satellite observations, we also have a partnership for data collection. It's a 30-year partnership with the French Space Agency, where we fly their instruments on our satellites, and the satellite becomes a relay to bring back data from climate stations, stream gauges, tidal gauges, and a bunch of living organisms that have transmitters permanently attached to them that beam up to the satellite. Because the polar orbiters give us worldwide coverage, and we're able to geolocate using these devices, using a Doppler technique. Next slide. And I will end on this, which is we've also been using our satellites as relay platforms for search and rescue beacons as part of a partnership that includes Canada, France, and Russia. And we're able to pick up the distress signal, beam it down to our satellite operations center, and then quickly determine which rescue agency to alert. In the case of the U.S., it's the Air Force on land, Coast Guard by sea, but we also pass alerts to other countries. And Abby Sunderland, whose name printed out fine on my printer, but apparently doesn't on this computer, who was trying to sail around the world at the age of, I think it was 16, and failed, turned on her distress beacon, and it was a NOAA satellite that was the first to pick up the location. And she was rescued and came to the NOAA Satellite Operations Center you see in the background in Suitland, Maryland. So with that, I turn it over.
Okay. Thank you very much. I think I learned a couple of things that I hadn't really thought about. I think we all did, that the partnerships matter well beyond saving a little money or doing joint research. There's lives involved, not only the search and rescue, but clearly the hurricane season. Satellites predicting paths of hurricanes is clearly one of the few things that NOAA and NASA do is directly in line with saving in human life. Okay, our next speaker is from the Department of Energy, Kathleen Turner. Dr. Turner is a program manager in the Office of High Energy Physics and the Office of Science in the U.S. Department of Energy. In particular, she's a program manager for non-accelerated experimental research in the Office of High Energy Physics and the Office of Science. Basically responsible for funding a number of universities and national laboratories in research, in R&D, fabrication, and operations of research facilities. She's also a researcher in her own right and participating in many of these experiments. She's worked at Brookhaven National Lab as a researcher before joining DOE in 2000. I first met Kathleen on JDEM on the Beyond Einstein study for the National Research Council, and one of the outcomes was it placed high priority on a joint mission between DOE and NASA and other agencies in dark matter. And Kathleen, I'd like to turn it over to you at this point.
Let's see, can I change with the slides with this, or? Okay, I'll try it. If it doesn't work, I'll say. Okay, thank you for inviting me to speak today. So I'm in the Office of High Energy Physics, which is one of the 6 offices in the Office of Science at the U.S. Department of Energy. So I'm going to just kind of go over our program for a few minutes and then talk about some of our partnerships. So the Office of Science supports research that has led to over 100 Nobel Prizes in the past 6 decades, and it provides 45% of the federal support of basic research in the physical sciences in the country. We support over 27,000 graduate students, undergraduates, and engineers, and support staff at 300 institutions, and we provide the world's largest collection of scientific user facilities to over 26,000 users each year. So the Office of Science, we're set up to build and operate experiments and facilities for the scientific community in the physical sciences. So there are 17 DOE laboratories across the federal research system, and the Office of Science manages 10 of these laboratories for scientific research purposes. And again, it's the single largest supporter of basic research in the U.S., and we oversee and we are the principal funding agency of the nation's research program in high energy physics, which is my field, nuclear physics, and fusion energy sciences. So in doing this, along with funding and overseeing the laboratories, we provide grants to universities and other institutions to use the facilities in our program. So now I'm going to go on to the Office of High Energy Physics, which is where I am. This is just a picture of Fermilab. Is this a laser pointer or no? I guess not. I don't know if that helps. Okay. This is a picture of Fermilab, the main building at Fermilab, and here's a picture of the accelerator rings at Fermilab. This is our flagship lab in the Office of High Energy Physics, and we provide over 90% of the federal support for high energy physics research in the U.S. And we design, construct, and operate these research facilities. Again, we support the researchers at the universities and labs to carry out the research, and we develop advanced technology and support the workforce now and for the future. So one thing I want to note is that in our mission as building and operating the laboratories and the facilities for the community, it is the job of the laboratories, the scientists at the laboratories, to come up with the ideas and the science and the technology to further the science and the experiments. So that's part of their job, along with coordinating with the university groups. In high energy physics, the university groups and the scientists at the labs work hand in hand. Another thing I want to note is, well, you can't really see it very clearly, but in front of Fermilab there's a row of flags, and there's about 20-something flags there, and they put up a flag of every country where they have users that are currently working at Fermilab. So this Fermilab from the beginning, from the early 70s, has been an international facility, as well as our other laboratories and programs. Okay, so what we do in our office is maintain the nation's competency and leadership in high energy physics research, and we establish the strategic plans to identify the scientific opportunities that are available in this area. We formulate, justify, and defend the budget requests to implement the plan, and we manage the funding to deliver the science. So in the Office of High Energy Physics, we've broken up the program into 3 scientific frontiers. One is the energy frontier, where we use particle accelerators at higher and higher energies to create new particles, new forms of matter, and to understand how the matter and forces interact with each other. So right now, you may have heard the Fermi Lab, which was the highest energy machine in the world, is actually being overtaken by CERN, the laboratory in Geneva, Switzerland, in the last couple of years. So we actually have a big program at CERN, so our researchers, a lot of them have been working over there for years. So the energy frontier has been our highest, where our highest support is, our highest amount of funding for years. But we're increasingly supporting research at the intensity frontier, and we're trying to move this program along because there's a lot of things, fundamental science that you can learn at the intensity frontier, where you have, instead of trying for the highest energy, you can try for the most intense beam of particles. And then what's been growing in the past 10 years or so, especially since the discovery of dark energy, is the cosmic frontier. And here we use ground and space-based experiments, and as well as underground experiments, I left that out, to make measurements to offer new insights and new information about dark matter, dark energy, and fundamental particle properties of any kind of phenomenon that we're getting from space. Okay. So most of our projects and experiments involve partnerships or agreements with other U.S. agencies and many foreign countries. Oh, I also had a problem with the sizing here, I guess. So the big point I want to make is it's not one size fits all in setting up these things. Our involvement from an agency point of view is, and our funding depends on the size of the effort, the stage of the experiment, which country is a steward of the experiment, how many countries are involved, etc. The typical process that we go through is that scientists at our labs and our universities, it's part of their job is to develop these experimental concepts with the technology development, and to develop the collaborations to do this science and make a proposal to the agency. And then, there's many different types. There can be we can be asked to make small contributions to another agency's experiments. Many times we have small contributions to experiments in Europe, Japan, all over the world, really, where it's a small group of researchers building one piece of the experiment and coming over and taking part in the science. It can be a major contribution that is being proposed for our office, or it can be proposed that we are the stewards, that we are the lead agency on an experiment. And there are also many other types of collaborations that our scientists come up with, and a lot of these astrophysics ones are collaborations where there's many different countries contributing to get an experiment done, and these can become very complex, as you might imagine. Okay, so so scientists develop these experiments, propose them to the agencies, they undergo review process, and then if we decide that we're interested in doing it, we start working on a partnership or agreement or whatever is needed with the other agencies. So I just have a picture here showing a map of the ATLAS collaboration. This is one of the major detectors at CERN for the Large Hadron Collider, and you can see they have collaborators from all these different countries, and this is over 2,000 scientists collaborating on this experiment, and many from the US. Okay, I'm not going to actually read all this, don't worry. So at the energy frontier, what's been going on for the last 20 or so years is the Tevatron experiments at Fermilab, at the Fermilab Tevatron Collider, where it's beams of protons and antiprotons going around in circles and colliding at different points in the beamline. And this is a picture of the D0 collaboration, showing all the flags from all the different countries where scientists are involved. And here's the Atlas collaboration. You can't see, but these are all people, all in these different levels here. So what's been happening is this Fermilab Tevatron Collider, it's kind of come to the end of its lifetime because at the energy frontier, the Large Hadron Collider in Geneva, Switzerland has overtaken that. So the way it's worked is that DOE has built and operated the facilities for the Tevatron, with other countries contributing to some of the detectors, but basically it's the major funding has been from DOE. The National Science Foundation also makes a lot of contributions. But DOE has been the steward and provided the operations of the accelerator, and the agreement has been that the other countries can bring their scientists, they support their scientists, and they can work on our facilities. Okay, it's completely open, and we are the stewards. And reciprocally, CERN has built and operated the Large Hadron Collider, and the agreement has been that DOE we have an implementation agreement with actually the National Science Foundation and CERN, and so we made major contributions to the actual collider. We built a lot of the magnets, and we made major contributions to the detectors. And actually the US is the largest collaboration outside of a couple of the European countries to the Large Hadron Collider and its experiments. So in the same manner as was done at Fermilab, CERN is operating the collider in return for DOE making these contributions to the construction of it, and DOE then, the DOE-funded scientists go there and get to do the research on it. So we've put quite a bit of money in this, close to probably almost 800 million, I think. Don't quote me on the exact amount, but a lot of money over the past 20 years to get this thing built. So the way we operate in the US is DOE and the National Science Foundation have a joint oversight group to manage the combined US contributions. And so we get together regularly and discuss the status of the US contributions and how we want to go forward. We also sit on the resource board at CERN, where all the partners at CERN and in the Large Hadron Collider meet regularly to discuss the status of the experiment and the agency support. So these have been very important in keeping the lines of communication open all along. Where am I? Oh, wrong one. Okay. So at the cosmic frontier, which is most of interest to this group, I just wanted to note that we get guidance from a number of different sources in setting up our program. Our main source of guidance is from our HEPAP, the High Energy Physics, I can't even think of the name of it now. Advisory panel, High Energy Physics Advisory Panel. This is our federal advisory committee. This is our official federal advisory committee, and that meets regularly to give advice to a DOE and NSF. It reports to both of us on particle and high energy physics. In October 2009, a HEPAP subpanel recommended an optimized program in particle astrophysics covering dark matter, dark energy, and high energy cosmic and gamma rays, and the cosmic microwave background. So any kind of science that we're involved in there. So another important thing that they did is develop the criteria for us to be involved. We can't be involved at this area of overlap with other agencies. We can't be involved in every experiment everywhere, because then we aren't being efficient in the use of our funds. We want to make a a large visible contribution to an experiment to really maximize the use of our funds. So what this panel came out with is that dark matter, the direct detection of dark matter, and study of dark energy are the highest priorities in our program. Then we also have guidance from the National Academy of Sciences. So along with reporting to NASA and NSF, the Astronomy and Astrophysics Decadal Survey report that came out last August gave recommendations to DOE as part of a coordinated ground and space-based dark energy program. So the recommendations for DOE were that DOE should partner with the NSF on a large synoptic survey telescope, LSST. This is the ground-based telescope that does dark energy studies. And also DOE should contribute to the NASA mission WFIRST. So an important thing they also noted is if projected funding levels are lower than was expected, than was assumed by this panel, they said that DOE's role is critical in LSST, and that should be our priority. And they listed some other contributions that we might want to make. So I'm just going to go over the 4 areas real quick. Just in the direct detection of dark matter, I wanted to note that most of these are partnerships between DOE and the National Science Foundation Physics Division. So we have a number of these underground direct detection dark matter experiments. I won't go through them all, but we also, in coordination with National Science Foundation, provide R&D and fabrication for the next phase of all these experiments. These are all smaller experiments that are all now getting to the limits of what they can do and proposing a next stage, next generation experiment. So we work closely with the National Science Foundation to coordinate the reviews and funding of our new efforts. And sometimes they're the steward of an experiment, sometimes we are, sometimes we're making contributions to experiments in Europe and elsewhere, but we're doing it in a coordinated way so that we don't want to start funding half of something and then they don't pick it up and vice versa. So we're actually, yeah. Okay. So for dark energy, so we've been funding dark energy actually since before it was even discovered. We were funding the group, one of the groups that discovered it, one of the 2 groups. And we've continued this work. We've continued to fund operations for several of the supernova studies, which were the first, which was how it was found. And we're also now providing operation support, and we did the instrumentation for the baryon oscillation spectroscopic survey, which is the primary survey on the Sloan telescope right now in New Mexico. So High Energy Physics Office and partnering with the National Science Foundation Astronomy Division, we partner on the operations of this experiment. And that's, you know, they're really doing well, and apparently they're going to come out with some exciting results by the end of the year. They won't tell me exactly what, but that's okay. Okay, then we, in partnership with the Astronomy Division at NSF, we're also building a new camera and data management system for the Blanco telescope at CTIO in Chile. So the fabrication is supposed to complete this year, and installation and integration starts, and data taking will start in 2012. So this has been a partnership from the beginning. You know, we have set up an oversight group where we meet regularly, go over the status, we plan our funding together, we plan our reviews together. It doesn't mean that we have the same review, but we coordinate them. Okay, so, and then there's, of course, the Large Synoptic Survey Telescope, which was recommended by ASTRO 2010. And HEP is working now closely with the NSF Astronomy Division to coordinate the schedules of how we can set up the project, how we could do the reviews, how we could do the funding. It hasn't been approved at either agency, but a lot of the work is setting this up from the beginning to move through the pipeline to get to the place where it could be approved. That's what actually, that takes much longer than once it actually gets approved and started, it seems. So as in all the other experiments that we've been doing with NSF, we set up a joint oversight group. We have regular meetings with the agency, and then the agencies together with the project office. Okay, so I did want to mention a couple more words about dark energy, since everybody has heard about JDAM probably. So we did develop a plan for a joint dark energy mission with NASA, in which NASA would lead the mission and DOE would contribute a major instrument, and both agencies would participate in the science. We signed a memorandum of understanding, and we had been holding weekly joint coordination meetings so that the agencies, as I said, could line up the processes for making agreements on funding and getting the project through. We set up a science working group to develop the concepts. So we were working very close, and as always in the beginning, there's bumpy roads because agencies do things in slightly different ways, but you know, I think it was working very well. But then it came to the decadal survey, and JDAM was not recommended, and instead they recommended WFIRST, which would do the dark energy science along with other sciences. Okay, so, and in this, NASA has the lead on WFIRST. We are supporting several people that were selected for their science definition team. And what has happened is, you know, before we had projected that we'd have more funding available. Funding has not come through, and so we are now planning to go forward with LSST, the ground-based experiment with NSF. And so for right now, we are not actively planning anything with NASA or other agencies to go forward in space. However, it's always open. Our community can propose efforts on future dark energy experiments, ground or space, and depending on available funds and priorities in the program, those will certainly be considered. And we are in regular contact with NASA. We're keeping up with each other what's going on. So, and the community has already come through with another ground-based stage 4 concept, Big Boss. So. Okay, at the cosmic frontier, we have several experiments with NSF Astronomy. Veritas is with NSF, and then 4 foreign partners that are making smaller contributions. The Pierre Auger Observatory, Cosmic Ray Observatory in Argentina is actually, I think, 18 countries with several hundred scientists working on that. So that's one where the collaboration more set up, got contributions from each of the funding agencies for different discrete parts of the experiment, and the collaboration kind of managed much more getting this all together than the agencies did. But we do have regular meetings, yearly status meetings with all the agencies. So that's an important thing, and we actually had a review of the operations with all the other agencies in the International Finance Board last year, and so that's been working well. Working with NASA, we've been working on the Fermi Gamma Ray Space Telescope and the Alpha Magnetic Spectrometer, and I'll talk about those more in a minute. And we're considering some other gamma ray observatories here. Oh, okay, I have 2 more. So, okay, so I'll just talk about Fermi Gamma Ray Space Telescope. We had an MOU with NASA that we built that our lab, SLAC, managed the fabrication of a large area telescope with DOE and NASA partnering on it with other foreign partners. And that's been working really, really well. As you know, you've been hearing, actually in the movie at the beginning of this session, they talked about the Fermi Space Telescope. So the Alpha Magnetic Spectrometer, this is a large, successful international collaboration led by Professor Sam Ting that we support his science program. It's got 16 countries and 600 scientists working on it. We have signed an agreement with NASA for the U.S. contributions, where DOE is the steward of the science, and NASA will provide has provided the space capability expertise, and it's going to provide the launch on the shuttle and operate it on the space station. So actually, this is scheduled to launch on the shuttle on April 19th. Okay, so we also have an agreement for providing data operations with NASA for the Planck mission in the U.S. Okay, so just the last slide, just Several important things we've found over the years in our partnerships all over the world is it's important to have international program coordination, and we have the Global Science Forum, we have, and other groups like this, the FALC, which is a global agency, a global group looking at the linear collider, holding regular meetings to just get all the agencies together to talk about their programs and to try to coordinate efforts. We have, with our major partners, international partners, we have annual meetings and agreements where we sit down and talk about how do we coordinate efforts and go forward. But especially once we decided to do a project or an experiment together, in the U.S. we set up these joint oversight groups to meet regularly and discuss issues and provide a primary point of contact with the project. And we also have found it important to have these finance and resource boards where we get all the funding agencies, not just the U.S. ones, together to talk about funding of the project and kind of make sure the funding is coming in a coordinated fashion. So just my important points are to have these regular contact meetings between the agencies and to have as much as possible written agreements for construction and operations.